Okay, so welcome to the second session on statistical learning theory. Just a reminder, there is a homework which is due next week, so please check the website and ask me questions, of course, if you have any. So this time the homework is only about programming. There's no question to answer, so maybe you will like it better. So let me just follow with the second lecture on statistical learning theory with the reminder. So remember what we said last week? We said that we observe couples, x, y, in nature. As usual, we have x in most situations, and we want to predict y. But we just assume that any pair of x and y's are distributed according to some probability p for those couples. And the other important thing that we have introduced is the loss function, which is basically a way to quantify how wrong a prediction is. So in the case of binary classification, it's quite natural to use the 0-1 loss. In the case of regression, one can use the squared loss. Given those two elements, we can define a function on functions. So again, this g here is a function from x to y. And we define a function on a function, which is the risk. And the risk builds upon the probability, the real probability, and the loss function. And it's just simply the expected loss under the probability for pairs y and x. And so we try to see if j of x matches y, and if it doesn't, we pay a price. And so we integrate this. So as we said earlier, one of the important things in inference is trying to find a function with a low risk. How low can we go? Well, this is given by the base risk. It's the lowest risk you can achieve. So it's the function. So it's the infimum of the risk over all possible functions. And we have proved that the Bayes classifier achieves the base risk. And what is the Bayes classifier? Well, it's simply the function which to an x assigns a 1 if the probability, the conditional probability that y is the 1 given x is bigger than 1/2, and it's 0 otherwise. This formula is really, really simple. You really have to, I'm sure you have all understood it, but it's really fundamental. It's just saying that if I have an observation, if I just if I just take the value of x, which is given at x here, and I just look at what is the probability that for that x, y equals 1. If it's bigger than 1/2, then I should say that it's 1. If it's smaller, it's 0. The same kind of rule applies for the Bayes estimator in regression. The Bayes estimator is just the expectation of y given 1x. So this is all nice. It's a nice theory, but unfortunately we never have access to p, so we will never have access to the Bayes estimator. But what we have access to in practice is samples. So here we have n points which have been drawn, n couples which have been drawn according to p. And then we form with this the empirical counterpart to the real risk, which is the empirical risk. The empirical risk is just the average over pairs y and x. What is exactly overfitting? Well, overfitting is pretty much can be summarized in this sentence. It's relying on the empirical risk to define your function, and relying blindly, exclusively on the empirical risk to define your function. So it's basically trying to look for a gn. So n here stands for a number of points. So for each number of points, you will have a different estimator, which is the minimum over all possible functions in some class of the empirical risk. And then once you have chosen that function, you realize that after, maybe because your estimator doesn't work, your machine fails at predicting things, that actually this estimation of the risk was really, really bad. So overfitting is somehow relying blindly on the empirical risk when looking for a function that you want to have low risk ultimately. Okay. So what we have discussed in the previous lecture is that, of course, we cannot consider the space of all possible functions. So usually we limit ourselves to a subspace. So if you remember this drawing, This was the whole space of functions. Maybe one among them here was the Bayes rule or the Bayes estimator. Since we are using computers, we need to restrict ourselves to one space of parameterized functions, big G, or here I probably wrote big G. Okay? And what we know is that among those functions, there is one which actually minimizes the real risk, the true risk. It's somewhere there. We don't know where it is, but it exists. So when we try to see how bad our function would really prove to be in terms of true risk with respect to the best possible risk, usually one splits it between two terms, which are the estimation error and the approximation error. Why is it important to split between two terms? Because this area here, this approximation error, it basically depends on the G that we have selected. Is FB very far from G? And this is quite difficult to control and to understand. So usually this is left a bit aside. The part that we can control better and understand better is the estimation error. Why is it estimation? Well, estimating is defining a function using points. And this is basically the error that you're making by using this estimation with respect to the best possible function that you could find somewhere here. So let me just start talking about bounds. So I think I should have defined this a bit earlier, so let me just go back to this word. Maybe some of you don't know the word. So what is empirical? What do I mean by empirical risk? Well, if you just look for the definition of empirical, you will find a few. Some of them go like this: derived from or relating to experiment and observation rather than theory, guided by practical experience and not theory. So this, I think, really qualifies what we're doing, which is that we consider empirical quantities, which are just computed according to observations, and we are not using the real theoretical quantities, which we do not have access to again. So for the sake of simplicity, some of the slides that follow will be easier to read if we use these notations, the following notations. So instead of using xi, yi as a couple always, we will just use a shorthand zi, which will be just one observation. So zi is one observation in nature of the couple. And z is the joint distribution of both x and y's. Why do we do this? Well, because it's a bit cumbersome to always consider the loss of a function g of x and compare it to y. So what we simply do now is define a function which is called the loss class, which is actually all possible losses induced by all possible g's in the function set big G or calligraphic G. So f is going to be a function which to a couple x, y just outputs 1 or 0. Okay, this is the Kronecker symbol. So this is 1 if g of x is not y, and it's 0 if g of x is equal to y. So this is the loss class. And if you make a mapping between one function g and one function f in the loss class, you will see that it's very easy to define the following notations. First, p of f, the operator p, probability p, will be the expectation with respect to p of f of xy, or I should have written maybe z here, f of z. And Pn of f will be the empirical expectation operator applied to f, which is just simply the average of f of x, I, y, I. So you can read this, of course, as P of f is equal to expectation with respect to P of f of z, and Pn of f is equal to the sum of 1 over n, y equals 1 to n of f of zi. Okay? So then it becomes a lot more clear that what we're just comparing is the empirical average of a function and its real average. Okay? So you will see very clearly that this PF, this real average, the true average, is actually the true risk of G, the corresponding function G. and the empirical average of F is just the empirical risk of G. So we're going to use probabilistic tools on F from now on and not so much on G, but always keep in mind that they are related. So what is the situation that we have? We have for every function F in this loss class, Pn of F is a random variable, which depends on a random sample of size n here. Okay, it's really important to understand that P is a deterministic function of functions in F. So this is a function of functions. P of F is a function of F, which is deterministic in the sense that there's no randomness involved. You know the whole probability. You have access to the whole probability. You can integrate. It's a big integral, but it's defined. Whereas Pn is a random function of functions. So here the randomness is somehow hidden in this little n, but n is more than just the number of points. It's also the whole sample of points of n. It's basically this whole thing. Okay. So since remember that we are in a probabilistic setting, so what we have access to is this, but we assume that this is itself a random sample of size n of IID points, identically distributed, independently, identically distributed points from probability P. So in terms of usually what we call this Pn of F varying over the whole function class, the loss class F, it's called an empirical measure indexed by F. So it's a family of values, real values, which are indexed by functions, and those values are random. They depend on samples, and samples change depending on the sample, of course. The theory which tries to see how fast P of F and Pn of F, so Pn of F converges to P of F as a function of the size n, is called empirical process theory. But again, here an important part is that we're not considering only the convergence of this on one particular function. We'll be considering the convergence of this over all functions. So we will discuss this later why this is important. So again, Pf minus Pn of F is just the true risk minus the empirical risk of a function G. It's just the expectation minus the empirical average. If you just look at the very first results in probability theory, you have that if those Zi's are IID, distributed according to P, then the strong law of large numbers says that the probability that this is equal to 0 as a limit, the limit of this is equal to 0 is 1 in probability. So when n is big enough, basically this will be almost surely equal to this. I mentioned last week another result which is called Hoeffding's bound. So Hoeffding's bound is a more precise quantification of this convergence. To obtain it, we need to have some assumptions. And one very important assumption is that the values of f of z are going to be bounded. So if we have values of f of z which are bounded, then we can have a better result. In our case, is this the case? Well, remember that f of zi, all of those f of zi's are either 0 or 1. So they're not even, they're bounded, but it's even better than that. They're just either 0 or 1, okay? Because it's a loss. Behind this, remember that for every f here, basically you have to think of there's a g function here, which mentions whether g of x is equal to y, g of xi is equal to yi. So maybe I didn't insist on this enough. Here we're only considering the classification case. Okay. So if all of those f of z's are between a and b, so here in our case it's a is equal to 0 and b is equal to 1, then there is a theorem called Hoeffding's theorem, which says that the probability that the absolute value, that is, the absolute deviation from P of f of Pn of f is bigger than epsilon, is smaller than this. So again, it's really important to see this clearly again. Here we have a probability. What is the random part of this quantity? There's only one random part. It's Pn of f. Okay? Pf is fixed. We don't know it, but it's fixed. What varies is the samples that we get. And this is the only Pn of f. So if you draw somewhere a value of P of f, so remember that this is a risk. And the risk in classification is necessarily between 0 and 1. Okay? And actually, well, it's between 0 and 1. So what we're measuring is there is a tube here with epsilon above and epsilon below. And we're just saying that the probability that Pn of f will be outside this tube is smaller than 2 exponential minus 2n epsilon squared, blah, blah, blah. So basically the probability that for a sample, Pn of f is here, it will be somewhere here, right? Pn of f can only be between 0 and 1. Basically, we're just saying that the probability that it is outside this tube, again, in terms of the sample, is smaller than this. So what can you say about this, which is interesting, this quantity here? Well, basically, the smaller epsilon is, well, the smaller this tube will be. And it would make sense that this probability goes somehow is at least 1 or even bigger than 1. And this is the case here. The epsilon goes to 0. This is equal to 0. So basically, you're saying that the probability is smaller than 2. It's not a very informative statement, right? But it agrees with the intuition that if you say, OK, what is the probability that this will be outside of this tube is if the tube is very, very thin, well, it's a huge probability, it will be 1. Now, this is not the really interesting part, right? So the interesting part is more when you make it a bit more challenging and you make this tube a bit wider. So if you make this tube wider, then of course the probability starts to decrease. Okay? And the very interesting part is more as a function of n, actually. N basically tells you that the probability that the average, empirical average, minus is outside of the tube decreases exponentially fast with respect to n. If you fix epsilon, if you have 5 samples, if you have 10 samples, the probability will be the square of what it would be if it was 5 samples. Okay? Did I say something wrong? Yeah. No, it's okay. So basically, with n, you will have an exponential decrease of this probability. So this is a really important result. So why is that much, much better? Well, it's much better because if you compare this to this, here we have absolutely no idea of what the influence of n is. Here we're just saying that in the limit where n goes to infinity, things work. But n is never the infinity, so it's useless. Here we're saying that the deviation of this from the true mean is explicitly controlled by n. And we only got this result by assuming that f of z is between a and b. So let me just try to illustrate this a bit more explicitly with an example. So you remember this this problem, which is just simply the probability, or the two variables, which are the height of someone and his or her gender. Okay. So here I have represented for males and females probability densities of the height. So of course, so you can see that for male it's a bit, well, it's not easy to see in 3 dimensions, but the probability that someone is 190 centimeters is not 0, whereas it's almost 0 for a female. Okay? So what is the task here if I have X and Y, height and gender? Well, I want to predict the gender of someone given the height. Okay? So I cannot see the person, you just tell me the person is 160 centimeters and I have to predict whether it's a male or a female. So those are the densities just in 2 dimensions. Again, as I was telling you, for males, the probability extends up to 202 meters. Of course, there's a very small probability here above, and this is for females. So assume for a minute that we have access to these curves. Okay, those are the real probabilities. If we have access to those curves, we can compute the risk, the true risk of any function, any predictor. Okay, so here is what I did. I predicted, I computed the true risk for one very simple class of functions, which are Heaviside functions or threshold functions. So imagine that the rule that I come up with is very simple. It's just below a certain threshold, the person will be a female, and above a certain threshold, the person will be a male. So or the opposite, actually. I could be using it the other way around. So below it would be a male, and above it would be a female. So this is a linear classifier, if you want. It's a linear classifier in 1D. Okay. So what is the variable of those that linear classifier? If I choose the fact that below the threshold it would be a female, and above the threshold it would be a male, this is the true risk of that family of functions. So does it agree somehow with intuition? Well, basically this is what is said here. So there is slightly, in the world population there is a slightly higher proportion of females than males. So if, for instance, you were to set a threshold at, let's say, 100 centimeters. So you would say anyone that is below 100 centimeters is a female, and anyone above 100 centimeters is a male. In practice, what you're saying is that you're saying that everyone is a male, right? Okay? Because most people are above 100 centimeters, so you will be saying that everyone is a male. And in that case, you will be missing all females. And that would mean that you're making a mistake of 52%. Okay? Now imagine that you're doing the opposite. You're setting your threshold at 2 meters 20. So you're saying anyone that is below 2 meters 20 is a female, and anyone that is above 2 meters 20 is a male. Then you're making a mistake for all males, because basically there's very few people above 2 meters 20, and so your error would be about 0.48. Okay? Neither of those two extremes are very clever, and actually it turns out that for this model, maybe the best possible threshold is somewhere here. This is the Bayes classifier. And it would be saying that someone is a female if he or she is below 171.5 and a male above. Okay? So this is just, I just have a function, I have it stored here in my computer. I know that this is a true density. It's very, very easy. You can look at the script in MATLAB. It's then very, very easy to just compute this function as a function of the threshold. Look for the minimum, and you get the minimum here, and that's the Bayes classifier. Okay? If you remember, in the last lecture, we actually computed explicitly the Bayes classifier. And we said that eta was this conditional probability that y equals 1 given x equals x, and this was the conditional probability. And the point where this conditional probability here goes above 1/2 is exactly 171.5. So everything is fine. So again, this is all in the case where we have access to the whole information. Okay? So unfortunately, we never have access to this. Okay? We all know that we only have access to this. So those those diamonds here are just the information that someone gave me, a measurement for a female that was this height, whereas those are measurements for males, okay? The blue circles. So I just have maybe, I think it's 30 points. And I assume, again, that they have been sampled from that distribution. So I never see this. I never see the curves. The only thing that I see is those diamonds and circles. Or this. Of course, depending on the day, depending on who collected, depending on where it was collected, etc., I will have a different sample every time that someone gives information. Okay? So remember that this is the randomness. Okay? This is the true risk, and there's only one. This is the empirical risk. It will depend. So let me just give you a small demonstration on MATLAB to illustrate all this. Okay. So here I have plotted a few things. So this is the true distribution, okay? This is the female, this is the male, and this is the joint distribution of x and y. Suppose my function, the one that I have decided to apply, is 165 centimeters. Okay? I will say that my rule is if someone is below 165, it's a female. If it's above, it's a male. So this is the plot of my function, right? It's 0 below 165 and 1 above 165. What is the risk of this function? Well, if I have access to the real information, remember, I have access to this blue curve here. I know I'm selecting this threshold. This is arbitrary, 165. So it's basically this value here, which I have represented here. So here, according to this distribution, the true risk, that is the number of mistakes that I would be doing on average, is 0.26549. It's not too bad, right? It's not, again, it's not the best. The best is more here, but that's acceptable. So what I don't know, though, what I do not have access to is, I need to do this, okay. What I do not have access to is these curves, right? Or the blue curve for what it's worth. The only thing that I have access to is those points here. So if I select 165, I can see how many mistakes I'm doing on those points. How many mistakes am I doing? Well, here I've represented the diamonds and the circles. So remember, circles are males and diamonds are females. So here it seems that my rule basically gets right all the males, but doesn't get right many of the females here. Okay? So what is the error that I'm making here? Well, the error that I'm making is 0.333333. So it seems that those diamonds here are exactly 1/3 of my sample. Actually, my sample size here is 30, so it means that here I have 10 diamonds which were misclassified. Okay? So now, I have told you that the true risk as a function of the threshold is a curve. What about the empirical risk? Well, this is the empirical risk. This is exactly the empirical risk for this sample. If I were to select one threshold in this area, I would be selecting basically some function here. So what would be the minimizer of the empirical risk in this case? Well, it would be, it's not unique. It's somewhere around here, right? It's anywhere between 175 and 176. For this particular sample, that's the best that I can get. Okay? What about the difference between the true risk here and the empirical risk that I got by selecting those points? It's 0.33. And the other one was 0.26. So here I'm actually it's an interesting situation. I'm overestimating my risk. 165 centimeters as a decision looks bad on the empirical risk here, but it's not as bad as what it really is if I were to sample a very, very large population. So let me continue and consider another sample. Someone gave me more information. In this case, here you can see that I'm making far less errors. It seems that this sample, this diamond here is a mistake, this round here is a mistake, but I'm only making 2 mistakes. So it's 2 out of 30, 1 out of 15. So the value of a mistake is 1 divided by 15. It's this. I don't know if it's exactly this. Maybe there's another one. And what is the empirical risk associated with that particular sample? It's this one. So you can see that this empirical risk here has a very, very different shape than the previous one. So if I only use 30 samples, I can get this, for instance, or I can get this one. Okay? They're pretty different, right? They're quite different from one from the other from the true risk. And here, this is the typical case where this is problematic because my sample here seems to work very well. Actually, 165 is very close to the minimum error, as you can see. It's very, very low here. And so it might make me think that 165 is a very good choice. But again, if I know the true probability, actually it's not such a good choice. So we can continue doing this process of sampling different samples, and we get different empirical risk curves. Okay? And then what you can start doing is basically drawing those crosses, and you will get more and more crosses, right? And then what you can start doing is plotting the deviation, doing it. And start doing it. So if you just start adding many, many different samples, each of those crosses basically represents a deviation from the true risk. Each of those red curves here represent a different empirical risk functional. Okay? And what you will observe, first, just a very simple question. How many values here? So if you really look, sometimes there are many crosses which have the same value, which are exactly on the same line. And it seems that those crosses are on discrete intervals. Why is that? Well, the empirical risk can only take those values, right? It can be 0, 1 over n, 2 over n, n minus 1 divided by n, and n. So whatever the size of whatever the sample that I get, I can make just a discrete number of mistakes. And so the empirical loss here will be among those. So this is why we will start seeing some values here which are all on the same line. So this can run for a while. What you can see also is that it seems that the red lines kind of giggle around a bit the true risk, but of course they don't match it. So this is a slightly different presentation that I was using last year. this would be the true risk. Those crosses would be the empirical risk that we have generated, computing samples. And those would be the frequency of deviations. And again, this just means that it's quite frequent to have a small deviation. So it's quite frequent here to have a small deviation to true risk. And the tail here is exponential somehow. So what happens when you only have 5 samples? Well, if you only have 5 samples, of course, again, you can only take values in 6 possible errors, n plus 1. Okay. So if you only build your empirical error using 5 points, each empirical error can only be 0, 1 divided by 5, etc., 4 divided by 5, or 1. And so you will see some accumulations here in those areas. 0, 1/5, 2/5, 3/5, 4/5, maybe even 1 more rarely. If you take 10 points, then again it's between 0, 1/10, 2/10, etc. And you will see this. Now remember what Hovding's inequality was saying is that the probability that those crosses here are far from this line here decreases exponentially with respect to 2 exponential minus 2 exponential epsilon squared. So the bigger n, the more we would expect to see those crosses here concentrate around the blue line, right? And this is indeed what happens. If n is equal to 20, we have this. If n is equal to 50, we have this. 100, 200. And so when n is equal to 200, you're sampling 200 points here. Then what you see is that the empirical risk is very close to the true risk. Of course, there are some cases where the deviation is not negligible, but in most cases, you have a very small difference. So again, the Hovding's bound is not telling us exactly how far those crosses will be from the line, but it's giving us an upper bound. It's basically telling us that a fraction of those crosses will be very close to the real line in probability. Okay? So how can we prove Hovding's bound? So it turns out that Hovding's bound was not the first bound proposed to study the concentration of random variables around their mean. There are other results which have been proposed before. The first one is of those results was Markov's inequality, which basically tells you that if you have a non-negative random variable in R, then the probability that it becomes very big, bigger than t, is upper bounded by the expectation of x divided by t. So this result is the first building block to prove another bound, which is called Chernov's bound, which you can use to prove then Hovding's bound. So the proof in itself is technical. So it's if you're interested, you can easily find proofs on the web. But what I really want to insist rather on the proof itself is that you really capture the idea behind this bound, this inequality. The probability that the deviation between the empirical and the real mean is big decreases exponentially with n. Okay? So if you find this hard to read, and at first this might be the case, you can use this other formulation which is different, which is that if you just substitute, if you just write that this is delta, and you invert, if you just write delta equals, and then you invert the value of epsilon as a function of delta, you get this. You get that for delta, which is positive, the probability that this is bigger than this epsilon is a function of delta, the inverse of delta. Again, I'm going to write it. So if I have like this, then you just write this is equal to delta. So then you have theta divided by 2 log is equal to minus 2 n epsilon square divided by b minus a square. And then this just helps you write, I think it's log delta divided 2 divided by delta, right? Yeah. So basically this is just log 2 divided by delta times b minus a divided by 2 and by n square root. Okay? And so if you just reformulate it the other way around, you can say that the probability that this is bigger than this quantity is smaller than delta. So if the probability that something is bigger is smaller than delta, it means that the probability that it's bigger, the probability that it's bigger is smaller than delta, it means that the probability that it's smaller is at least 1 minus delta. Okay? And then we have something which is a bit more intuitive sometimes, which is this the following statement. The quantity Pn of f minus Pf, the deviation, what we're interested in, is smaller than a quantity, which depends on delta here, with probability at least 1 minus delta. So typically you set delta is equal to 0.5 or 0.1. And then you will say, with probability at least 95%, the deviation between Pn of f and Pf is smaller than the square root of log of 2 divided by delta divided by 2n. And this gives a very intuitive quantification of how this Pn of f converges to Pf, which depends basically on the square root of 1 over n. Okay? So whenever you think about Pn of f and P of f, sample size n, always think that there is an upper bound which tells you that Pn of f minus P of f is smaller than a quantity So this is the result of Hoeffding's bound. And the constant, so let's say a constant which depends on delta, with probability at least 1 minus delta, you will have that Pn of f minus P of f will be smaller than a constant which depends on delta, and then 1 divided by the square root of n. So this bound basically evolves as 1 divided by the square root of n. Meaning it doesn't evolve linearly or as 1 over n basically. If you add from 1,000 point, then to get a better a twofold, if you want, improvement in this bound, to divide this bound by twofold, you need to multiply it by 4, the size of n by 4. Okay. So it's a very slow convergence somehow. Well, it's not really slow. It's in square root of n, basically. So what is exactly the interpretation that we can make in terms of risk? So again, functions f that we have been considering in the last class only take 0 or 1 as values. So b is 1 and a is 0. This b is 1 and a is 0. So this term just cancels out. And we can now say that for any function g, if you give me one function g, and then you give me one sample, the risk, so the absolute value of the risk minus the empirical risk, but let's just take the direction which is interesting for us, which is to say that the real risk will not be larger with probability at least 1 minus delta than the empirical risk plus this quantity here, the log of 2 delta divided by 2n, of the square root of that. Okay? Again, what is the probability? Where is the probability coming from? It's coming from the sample, which has been drawn. Okay? So this seems to solve somehow our problem, right? The problem that we have in mind about bounds was that we wanted to be able to say for sure that the risk of a function g, the true risk of a function g, was not much worse than the empirical risk of a function g. Okay? Do you think this works really? You can use Hufting's bound in your on a data set. So, for instance, imagine the following situation. Here I'm giving the answer, but okay, this is a bit complicated. Let me just first give you an example. Imagine that I give you 1,000 points. Okay, again, I'm giving you this very simple problem. I'm giving you 1,000 points. Actually, maybe if I use the MATLAB illustration, it might be better. Here, what have I done exactly? First, I defined one threshold, 165, and then I started showing you that if you plot the empirical errors here, they will fluctuate around the true risk. And there is a very big difference between the true risk here and the empirical risk curve here. And the result that I've been telling you is that basically those crosses here, if n is big enough, they will be not too far from the true risk. Okay? But what is the big difference between this approach and what we do in machine learning? Can anyone tell me? Again, here I have set the threshold at 165 centimeters. I'm looking for a function which predicts the gender of someone according to his height, his or her height. I set the threshold at 165, and I say this is going to be my function. And then I'm discussing the differences between this and the true risk. Okay? Is this what you would do in machine learning? Can anyone highlight or tell me what I'm doing that's a bit strange for someone trying to do machine learning? Again, the problem is the following. There is a data set. There is a problem which is predict the height of the gender of someone given his or her height. I assume I have a data set. I'm trying to predict a function that will do that. And I'm trying to see how far I'm overfitting. Basically, what is the difference between the true risk and the empirical risk? Okay? And I want to use bounds, such as Hoeffding's bound. So to do that, I just said, okay, I set my function to be 165 centimeters. Okay, that's going to be my classifier, and now I can use Hoeffding's bound and say that those crosses here cannot be too far from the empirical. So if I get one error, empirical error, then I can come up with a nice theory to tell me that it's quite likely that it's not too far, etc. Does this sound right to you? And then I go and I say, okay, here is my classifier. It's 165 centimeters. Would you have any criticism if I were to go and, okay, 165 criticism is good, and actually I know that 165 is not too far. The empirical error that I get on this data set you gave me is 0.16, and it's not too far from the true risk. I don't know the true risk, but I can tell you that Hoeffding's bound tells me that it's not too far from the true risk. Isn't there anything that's flawed? Again, I really want you to understand this because this is a key thing here. I have a data set, okay? I'm choosing the threshold to be 165 centimeters. What is the error of that data set here with that threshold? I just counted. Oh, it's 4. So this is probably maybe here or here maybe. One of those. And then I can tell you that, oh, I'm not overfitting because Hoeffding's bound tells me that this cross here, the empirical error, is not too far from the true risk. In some sense, I'm not overfitting. Here is the classifier. It's 165. Is there anything that I did that's a bit strange? No ideas? Well, the first question that you should ask is, did I learn anything? How did I choose 165? I just set it before, right? I just said, okay, the classifier is 165 centimeters. Now you give me a sample. I am a probabilist. I can tell you that the empirical error on that sample is not too far from the true error because Hoeffding's bound gives me this concentration inequality. And here is my classifier. I chose the function without looking at the data. Okay? So what happens is the following. Hoeffding's bound holds if you assume that you have one function f, and then you will see some samples which will start to rain, if you want, drop on you. And then for each different sample, you will have a different estimate of the empirical error. And this just tells me I can use Hoeffding's bound to tell, well, this is not too far from the true risk. Basically, what I'm doing is I'm studying from the viewpoint of this function here, 165 centimeters, and I see red curves here and there and there and there and there, and then I'm just saying I'm not too far from them. But this is not what we do in machine learning, right? We have one sample that comes. We estimate a function using that sample. But then we cannot use Hoeffding's bound on that sample, right? Basically, we cannot do the following. We cannot do this. This is what using Hoeffding's bound in machine learning directly would mean. This is the sample. This is the empirical error. Okay? Empirical error for that sample. It's a different curve than the true error, okay? We don't know this. What do you do in machine learning when you apply an algorithm, when you apply regression, SVM, etc.? Usually, if you're not regularizing anything, you look for this point, right? You say, oh, this is an error that depends on the parameter. I am going to look for the parameter which minimizes the error. This is the empirical error that's minimized. This is what I'm going to use. 175 centimeters. Okay? But then, if you do that, you cannot use Hofstad's bound to say now, oh, by the way, Hofstad's bound also tells me that this error that I get here is not too far from the blue. Why? Because you have defined your function, the threshold, as a function of the sample itself. Okay? If you didn't get this, it's important that we get it right. So I just want to make sure some of you at least got it. Okay? Hofstad's bound says for one function, if I have samples, the true risk and the empirical risk will not be too far from each other using this exponential term, etc. But this applies only for one function that I have chosen before, and then I see samples coming up after. If what I do is, there is a sample coming, I choose my function, and then I'd say, oh, I can invoke Hofstad's bound to say that actually the empirical risk is not too far from the true risk, and everything's fine, then this is false. It becomes false. Okay? It's an important distinction. Okay, so I let you think about this, but this is probably the most important point here in this lecture. So what do we need to do to still use those tools? So let me just, for instance, give you an extreme case of overfitting. Imagine that you have the data, so someone gives you a sample, and then you estimate GN. And again, remember that one of the things that we have, the problems that we have, is that we don't know exactly what is the difference between the true risk and the empirical risk. I'm sorry, I forgot an empirical here. So let's say again that we define the stupid function, the one that learns by heart the database. Remember that the one that learns by heart the database has an empirical risk of 0. Okay? It's this stupid function that says, okay, we'll say that everyone is a female, except if the person has exactly the height of one of the males that I have seen in my database before. Okay? So this function has 0 empirical risk. Do you think you can invoke Hofstad's bound on that? Well, of course you can't. It would be really very optimistic. The reason you cannot is that you have built, again, your function using the database. So now you cannot pretend that this database was sampled independently from your function. Okay? So here is what we are going to do, which is more important and works better. We are going to study the supremum, the biggest gap between P of f and Pn of f over all the functions in the loss class. So what is exactly the idea? Well, imagine that I have, again, this is the function, the set of all functions. I'm going to consider my function which is the loss class. There is one curve somewhere which is called P of f. From the viewpoint of one particular function, so this is f, I can tell you, so those are empirical risks, okay? There's many, I mean, you can draw an infinite number of them. Now, let's look at this. This is P of f. And those values here are random Pn of f. Okay? So what Hofding's bound tells me is that basically, if I draw, if I have another color, if I draw a tube of width epsilon, 2 epsilon, sorry, around the true P of f, then the probability that those yellow ones are outside decreases very fast. Or if you want, the probability that with probability at least 1 minus delta, those pink ones will be somewhere there. Now, if I want to be able to use one particular curve, so I should, what we do in machine learning is never that. What we always try to do in machine learning is, okay, there's a real curve. We have access to one sample. Okay. What we do in machine learning is that we use that sample to define g of n. Okay. So here we cannot use Hofding's bound on this on this error here. So let's say f of n. Sorry, the f that corresponds to g of n. We cannot use Hofding's bound on this error here. However, what we could say is that this gap here will be always smaller than the supremum over all possible gaps in my function class. So this is the idea of the uniform bounds, is to say, okay, if I cannot use Hofding's bound in a machine learning setting where I use the sample to learn the function, then what about giving an upper bound for the whole possible set of functions? So this is it's quite violent. It's a very strong. I mean, it's a very loose approach, but it will work. We will basically say that, okay, if I cannot play with the very same data set than with to select the function and then compute Hofding's bound, I can still, however, say that the difference between RRG and an empirical risk of Gn will have to be smaller than this one, than the supremum, necessarily. And in that case, if we can come up with a bound for this quantity, so the supremum over f in this function class of P of f minus Pn of f, then I can do both things. I can estimate my function Gn using the sample and use this bound. Okay? So let me just give you a very simple example where this can be applied. Imagine that my set f here is just two functions. So I'm going to write f1 and f2. So my set of functions f is just two functions. I have the true risk here. Let's say I have the empirical risk. So if you're learning from data, so this is Pn, and this is P. if you're learning, which of the functions should you select? Which one is the one that you want to pick between f1 and f2? Anyone? Okay, we'll have to ask with the clickers. No one has an intuition of on which. This is the empirical loss. This is the true one. We don't know it. So the only thing that we actually have access to is this. Which of f1 or f2 seems to be more likely to be useful? Okay, I don't know if you're shy, being shy, or maybe you don't understand, so I need to check. Okay, so 1 is 1, 1 is 1, and 2 is 2, okay? So this is just a safety, sanity check to be sure that some people are following what's happening. So again, this is the empirical loss. This is the true loss, the true risk. We can only choose, our function class is just two functions, f1 and f2. Which of those two is more interesting? Okay. Okay, 10 people could have done better, but at least 8 of you got it right. So of course it's f2 because the empirical loss here is lower. Okay. I'm just saying that sorry. If you just compute it here, it's here. If you compute the empirical loss of this, it's here. So this is Pn f1, Pn f2. And of course we want a low empirical loss, so it's nice. So now, given this, consider the following. So it's a bit abstract, but think about this. Imagine that I am drawing the set of samples of size n of my probability p. Okay, this is a big set of samples. Each point here is an x, I, y, I, or zi, maybe zi, let's say zi, is a z1, zn. Okay? Each of them is different. So what you can see is that if you consider all possible samples according to this probability, well, you have a huge set of samples. Each point is a sample. You can draw two sets, which are C1, and this is, well, I'm just writing it as a connex set here, but it has absolutely no reason to be connex. It's just one set of points, which are all the samples for which Pnf1 is further from Pf1 than epsilon. Okay? So this, if you want, is the set of all bad sets, all bad samples. It's all the samples for which the deviation between the true mean and the empirical mean is bigger than epsilon. So it's C1, I should maybe write it C1 epsilon. And let's write another one, which is C2 of epsilon. Okay? So what can you say about C1 epsilon and C2 epsilon? Well, we don't know a lot about F1 and F2, but maybe for some samples, both F1 and F2 have empirical means which are far from their true means. And this is here, it's the intersection, right? Basically here we have all the samples for which the empirical mean Pn F1 is bigger than epsilon and Pn F2 is bigger than epsilon. So C1 and C2, those are the sets of bad samples. So now it's actually, you can use Hovding's inequality on each of those sets. What does Hovding inequality tell us exactly? Well, it tells us that the probability of C1 is smaller than some delta. Okay? If epsilon is equal to b minus a square root of log of 2 divided by delta divided by 2n. Okay? If epsilon is equal to that quantity, then the size of this C1 cannot be too big, right? If you let n increase, then the size of those sets here will shrink, basically. It will be the sets for which we make a big mistake. And of course, this has got to shrink if n goes to infinity. The same thing can be said about C2. Okay? Here, delta is exponential minus 2 n epsilon squared. What you can say is that if an n-apple, so basically a sample here is in either C1 or C2, that is in their union, then you either have one or the other which is bigger than epsilon. And remember that what we're trying to quantify is the supremum, the behavior of the supremum. So if you have either one of the two which is above, it means that the sup is above epsilon, right? So what you can say is that the probability of this set, this is the union bounding probability, it's the very elementary property of probabilities, Sigma algebras. The probability of the union of two sets is smaller than the probability of the two sets, so it's smaller than 2 delta. So what we're saying is that if I pick a point in C1 union C2, then the supremum is at least bigger than epsilon. Okay? And what is the probability of this? Well, we know that it's smaller than the sum of those probabilities, so it's smaller than delta, 2 delta. So with probability smaller than 2 delta, at least one of F1 or F2 will be such that, sorry, it's PFI minus PNFI is bigger than epsilon. So this is the idea of the union bound. Imagine now that I don't have only, I'm not restricted only to 2 functions, but my set now is big N functions. Okay? I want to check time. Imagine now that I have N functions, where we can do exactly the same thing. We can start drawing sets. So this will be C3, C4, C5, etc. So each of the Ci's are the sets for which the function, the empirical average of the function deviates from its true average by more than epsilon. Of course, the probability of the union of all this is smaller than the sum of the probabilities. So if I take one point in this union, I know for sure that one of the functions will be far. For one of the functions, the true mean will be far from its empirical mean. And since the size of all this is smaller than the size of all So basically what I'm saying is that the probability that there exists a function here such that Pf of f minus Pn of f is bigger than epsilon is exactly the probability of that union, right? Any point in that union is such that the supremum, there exists one which is bigger than epsilon. So the probability of this happening is exactly the probability of the union. But we cannot easily compute the probability of that union. So what we do instead is we use the union bound, which says that the probability of the union of a set of sets is smaller than the sum of their probabilities. So that's probably where we're losing a lot of precision here. We're basically saying that the probability of this set here that this shape, the probability of this thing here, is upper bounded by the sum of all those the volumes, the probabilities of those potatoes. So this is the biggest loss, if you want, that we're making in precision with respect to Hovding's bound. This is the price we're paying with respect to Hovding's bound for just one function. So if you just take the sum of those probabilities, then you would have that each of those sets here has probability has size delta, right? Has probability delta by definition of Hovding's bound on one particular function. Each of those potatoes here is exactly of probability delta. Is upper bounded by delta. That's the meaning of Hovding's bound. So this here, the sum of n terms for which each of them is upper bounded by delta, is going to be bounded by n delta. And so remember that delta is just exponential minus 2n epsilon squared. So what we get is that for a family of n functions, so n yellow crosses here, the probability that one of them has a deviation which is bigger than epsilon is actually smaller than n times exponential minus 2n epsilon squared. So what is the big difference between Hovding's bound, the way we presented it here, and here? Well, here there's just one very micro difference, which is that I removed the absolute values here, but this is not a very important detail. The important thing that you have to see is that the probability that P of f is actually much bigger. This you should read this way, right? You should read it as what is the probability that the true risk is bigger than my empirical risk plus epsilon. Okay? This here I can compute. This I can never compute. But what is the probability that it's actually much, much bigger than the empirical risk? What is the probability that I'm doing overfitting? That's the question. The question is, what's the danger, if you want, that PF is really much bigger than the empirical risk? And if you estimate a function in a finite set of functions, then you're paying a price of n times this. So this was Hovding's bound, the leading term of Hovding's bound. If we just scale up to n functions, then it's just n times that term. It kind of makes sense. Equivalently, if you want to invert it the way we did it with delta, you can say that if I have g1 to gn functions to choose from, then with probability at least 1 minus delta, for any function in that set, the real risk of that function will be smaller than Rn of g, the empirical risk, plus this term here. So now here we are in a safer zone, if you want. If you have to choose from 10 functions, you give me one sample, I pick one of those 10 based on that sample, I can still use this bound. Because this bound tells me, well, okay, I choose that function based on the sample, but my bound basically is valid for any function in the family. So it will work. So in that case, you can always say that the true risk will be smaller than the empirical risk plus this quantity. Okay? So of course, imagine that n is 10 million. Does this bound make a lot of sense? Well, no, because maybe this is going to be far bigger than 1. Maybe it's going to be 2 or 3. So you know that this is always smaller than 1 by definition. And my bound will tell you, okay, something that's smaller than 1 is smaller than 0.3 plus 25. In that case, it doesn't really make any sense. Okay? So bounds do not always make sense. Okay? So there are some cases where this will be small enough that this would be a useful statement if you want. So what can we do now? Well, this is the same idea. This is just what I said now. Oh, no, I think this is slightly different. Basically, if you follow the definition, remember that within the function class G, R of G star is the minimum. G star is basically the minimum function with the true risk, with respect to the true risk. And what we just proved here is that for that G star, the true risk of the G star is smaller than the empirical risk plus this supremum. And so if we combine this inequality with just simply this inequality, so here I'm just saying that Gn, you remember, is the minimum of the empirical risk. It was the bottom of our red curve. G star will not be at the bottom. It will be somewhere near the bottom maybe, but it will not be near the bottom. So this, since this is the minimum, this minus this is positive. So if you combine R of Gn, so remove R of G star plus R of minus R of G star plus R of G star, then you add this term here, then you will see that you can basically compute a very simple bound which tells you that the risk of Gn is smaller than the risk of G star plus twice this bound here. So what we just computed is a different bound now, which tells us that here we just computed a bound with respect to the difference of the true risk of R of G with respect to the empirical risk of Rn of G. And now we have computed a different bound which tells us that the true risk of our minimizer, the function we have computed, is not too far, maybe, if this is small enough, from the risk of the best possible function in the function class. So this is a slightly different result. So what can we say? Okay, so let me just very briefly talk about this slide, and then we will. No, I will continue. I will start from this slide next week. So again, homework next week. If you have found this a bit challenging, then please go again through the illustrations. You can check the script which helped me generate those curves here. You can check it directly on my website. And please do not hesitate to ask questions after the lecture. This is the key part. And there is another, I will put a link on my webpage to a nicely written tutorial on this topic. So so please give me your homeworks before, I think I said Tuesday noon maybe next week. And again, if you have questions on the homework, do not hesitate. Thank you.